both data ingestion and what we're going to talk about today, which is data visualization. I'm Jana Beck on GitHub and in most other places, including the React.js Slack. So feel free to reach out after this talk. I hope it's going to be a conversation starter. And here's a link to the slides if you want to follow along right now. They're already up. But before we dive in, I want to give you a little bit of a warning. I just want to be explicit about the fact that my goal here is to talk through some of the challenges and problems that I've been thinking through as I think about what the next version of our data visualization library at Tidepool might look like. So what this means is that everything I'm about to talk to you about is pretty preliminary. We're going to be talking about thoughts and ideas and experiments that are under construction and unproven. But even though these ideas are unproven, I hope that seeing what it looks like to think through implementing the Flux architecture for a large, complex, pre-existing real-world application will be useful. This isn't some little to-do MVC example. So our data visualization library at Tidepool is called Tideline. We use it to create all the data displays in our main web app Blip. I'm going to walk you through just a little bit of its functionality briefly so you have an idea of the size and scope of the task that we're talking about. So Tideline started with this one-day view. It's a horizontal scrolling timeline showing 24 hours at a time, with some summary statistics that update as you scroll along the timeline here at the bottom. The 2-week view has also been in the app. We're about to switch to it. It's been there since the very beginning. It's a reverse chronological vertical scrolling summary of a subset of the data. Since then, the app has gotten larger and larger, and now we have this trends view showing days of data layered into a summary. And then there's also a simple insulin pump settings view that we're going to get to in just a second. Here it is. And from any of these summary views, double-clicking on a piece of data brings you back to the daily view for the day of the event that you just clicked on. So the key thing here is that the different data views crucially share state. In particular, the date navigation is preserved or sort of translated across the different views. And then some of the components, like these statistics widgets, as we call them, those are also common to several of the views. So for these reasons, I've started to think about this project more as one sort of meta data visualization with a variety of surface manifestations, rather than as a collection of separate visualizations. So what I'm going to talk about today is the current progress of my thinking with regards to managing the state of that big meta visualization using the Flux architecture. But first, a little metaphorical aside about sandwiches, and I can't be accused of cruelty for making you hungry since you just had lunch. So what we have here is like the makings of a peanut butter and jelly sandwich, right? And now this is an Elvis sandwich. It's peanut butter, banana, and bacon toasted. It's probably the best peanut butter-based sandwich, in my opinion. But if you're in a diner and you want to order an Elvis instead of a PB&J, you don't have to give them instructions for how to fry bacon in order to order one. That's just not how we order things. We have better interfaces for that. In fact, we have interfaces so good that you can order a naan pizza with left beef, as Reddit famously proved. So you don't have to explain how to create this in order to order it. You just have to describe it. So how is this relevant to the problem at hand? Well, to put it sort of a little too simply, the strategy that I'm going to introduce to you is that I want to make the developer's experience of configuring a complex data visualization, and possibly the user's experience as well. This allows for the possibility of that. I want to make this much more like the naan pizza with left beef experience, where all you have to do is describe exactly what you want in a simple but powerful interface. And you just leave all the implementation details, including the procedural details of how to create it, defined elsewhere. So now we're really going to dig in, and I'm going to show you what the problem is. And to do this, I'm going to introduce you to D3 a little bit along the way. D3 is the JavaScript library that anchors the most commonly used tool set for interactive data visualization on the web. It stands for data-driven documents. So we're going to talk about a few things that are specific to D3. And I believe that they're a good illustration, but also a lot of this kind of applies to any front-end client application with a significantly complex user interface. And then, so you might ask, what do you mean by complex? For me, the definition of complex is basically that the same data, the same information is being displayed and maybe even potentially changed in multiple places in the same UI. So we've already seen this. This is what's happening with the data that you're seeing in the timeline, and then the updates happening in the statistics widgets, because those are reflecting the data that's currently in view. OK, so now we're getting into the D3 stuff. As a tiny introduction to the ideas of D3 that are relevant here, I'm just cherry picking a bit from one of the fabulous intro articles by Mike Bostock, who's the primary author of D3. So this article, and it's linked here, is Let's Make a Bar Chart. So the problem is how to turn a small array of data into a bar chart for easy visual comparison. The straw man solution that's raised in the article is to hard code it in HTML, where you hand calculate the width that each div should have in order to represent each item in the data array. Obviously, this doesn't scale. So you can do it better with D3. Instead of manually creating the divs to represent each item in the data array, you can use D3 to bind the data to child divs of the main chart div that you've set up. D3 will actually create these divs if they don't exist yet. That's what this enter call is doing. And we can also assign the visual attributes that we want the divs to have with D3's style and text methods, here and here at the bottom. So the former sets the width of each bar programmatically according to the value of the datum, and the latter adds the labels showing the value of each datum within each bar. So yay, we have a bar chart. I mean, not really, because I hard-coded this in order to put it in the slides, but you know. So now let's focus a little bit on a couple pieces of this from the previous code. So this is the append and style methods from D3. So these methods create the divs for each bar and then assign them the properly scaled widths. And I'm actually, D3 has great utility functions for like creating scales for your data that I'm not using here just for simplicity. But the question here is, how would you do this in pure JavaScript? And it's not really that hard. It's just a for loop. So the question is, what's the difference between these approaches? And basically, the D3 version is quite a bit more declarative than the for loop version. With D3, you don't have to specify the operations in the DOM. You specify the result that you want, a div added for each datum with a width 10 times the value of the datum in pixels. So to give you a preview of what's coming next, I'm about to complain about the fact that some patterns in D3 are not very declarative, and they're too procedural. And just now I'm saying that it is declarative. And the truth is that it's both, and I don't think that this declarative procedural or declarative imperative distinction is all that black and white. It's kind of a continuum. And this is like, whatever, kind of a tiny little bar chart example that's pretty boring, right? Like, how does it get more complicated? And one of the biggest places that I've noticed that it gets more complicated is when you're adding interactivity. So bear with me on this tiny bar chart example for a little bit longer so that we can consider what happens when we add a little interactivity. So what if we want the value of the datum corresponding to each bar not to appear in this label on the bar that's kind of visual clutter, but maybe we want it to appear on hover in a tooltip? So what's here is sort of the most commonly recommended pattern in D3 for adding tooltips to elements of a visualization. So you're binding listener functions to the mouse over and mouse out events. So here the mouse over listener that you'd write in here would insert the tooltip into the DOM, and then the mouse out would remove it. And now I have to pause and give a big hat tip to Nico Harry, who's a former colleague of mine. And he was the first to sort of point out this issue to me. And the issue is that doing this DOM manipulation in the listener functions bound to the mouse over and mouse out events is basically where you're veering back into procedural territory with D3. So of course, D3 is still giving some nice syntactic sugar. We're not actually using any of the browser's DOM methods. But essentially, we're manipulating the DOM more or less directly in response to an event. And that kind of makes me do this. Like, it's a huge red flag. And even worse, the state of the visualization with respect to the user's interactions is totally hidden. It's encapsulated deep down in that D3 code, and it's not exposed in a developer-friendly way for testing or for design iteration, sort of, et cetera. So back to this hat tip. The link here is to a blog post of Nico's, and that's where he discusses this problem and suggests the alternative of using the D3 event listeners not to draw the tooltips through DOM manipulation, but instead to just add the data point that you're mousing over to an array of focus objects, and then you pass that array of focus objects down to another either completely separate D3 module or maybe a React component that does the rendering of tooltips. So the idea that I'm presenting today is, in a lot of ways, nothing more than a logical extension of Nico's idea. So I'm advocating managing all state in a complex data visualization like this with the Flux architecture of one-way data flow. So that means making all aspects of the state of the visualization explicit, with nothing buried deep inside these D3 rendering modules. So instead of binding the mouse over and mouse out events to listener functions that manipulate the DOM, I'm just going to start binding them to Flux action creators. The best thing about this solution is that it's totally agnostic about how you're going to display the focus data. So you might even be able to do something like, if you're in a browser, on a desktop or on a laptop, you draw a tooltip. But if you're on a touchscreen tablet, maybe you want to take that array of focus objects and render that information in a sidebar, because tooltips are kind of a weird interaction on touchscreen displays. So that's one place where I kind of ran into these issues with common patterns in D3. There's another one that sort of doesn't make me super happy right now. In another article, Mike Bostock builds an argument for his recommendation of how to write reusable visualization code with D3. And it all boils down to this, which is a direct quotation. Implement charts as closures with getter-setter methods. And this is actually how much of D3 itself is written, and it's also a pretty familiar type of API for anyone who's ever worked with like jQuery. So there are a lot of advantages to this. But the problem, or at least my problem, is that at a high level of complexity, this getter-setter API gets really difficult to work with. So this code here is a snippet from the chart factory that we use to create our daily view with timeline in our application Blip. And so there's a whole bunch of steps here. So we call each horizontal section of that timeline a pool. So first I'm creating a bunch of new pools, and I have to pass in a bunch of information like the label, and the weight is like the vertical height weight, how much of a gutter it gets, all this kind of stuff. And then before I do anything else, so I do this for a bunch of different pools, then before I do anything else, I have to call these methods to arrange the pools. This is like figuring out what height everything is actually going to end up based on those weights. Setting up some layers for annotations, which I won't get into what those are, but they have their own kind of tooltips, and then our other tooltip module. And part of this is due to the restriction of most people use D3 to create visualizations with SVG, and that's what we're doing. And SVG has no z-index, so you have to use layering to control where things are rendered. So these layers for the annotations and the tooltips. And I'm sorry, I was scrolling the wrong display. There we go. These layers that are getting created are have to be created later. So it's only after I've created those that then I can actually sort of create the specific tooltip layers for each type of data. And so you can see that this is pretty complicated. Instead of ordering a pizza, what I'm doing here is closer to describing how to make it. And the worst of it entirely is the places where there's a strict sequencing of steps. Because even as the primary author of this library, I don't even remember where some of those strict sequences are. And so what I need instead of this is a way to describe the configuration of a visualization entirely statically. And getter setter methods just don't quite cut it for this. So every setter is a function that's executing when I call it. And it's rooted in that private encapsulated context of whatever state the visualization is in when I call it. And so that's why it may or may not behave as expected if I call it out of the sequence that the original developer had in mind. So basically the problem, like to sum it up, is too much encapsulation and too much implicit state. So since my problem is too much hidden state, the Flux pattern seems to be a natural fit with its emphasis on state managed by stores at the highest level of the application and information trickling down from the top, so that down from the top to the components that need it. So to illustrate how I see this working, let's talk through it with weather data, basically because this is something that you're all familiar with, unlike the diabetes data that we deal with at Tidepool. And weather data is also a pretty good example because there's a lot of it, and you've all probably seen many, many interfaces for displaying it. And here's a small list of common types of weather data, just to prove to you that there's a lot of stuff here. So there's things like cloud condition, high, low temperature, and you can have actual highs and lows or predicted highs and lows, the feels like temperature, precipitation, so the type, snow, rain, the likelihood, humidity, wind speed, and direction. These are all possible candidates for display and visualization, and I'm, of course, even leaving out stuff like barometric pressure, etc. Coming at it from another angle, we also have a bunch of different factors that may act as a filter affecting which data types are actually relevant for visualization or display in various contexts, like different types of views. So one of those, maybe a slightly one that you're not used to thinking about, is location. So I'm going with a Utah theme here. If you're viewing weather data from Moab, maybe you would want to de-emphasize humidity and precipitation because those things are just not very common there. Or if you're a skier like me and you're really interested in the weather for the Cottonwood Canyons, best snow in the world here in Utah, you have a different set of priorities for your weather display. And this is a link here actually to an app in a broad term. It's a weather blog about the snow here in northern Utah. So another view determinator is time. So if you're viewing past weather data, predicted high and low temperatures are probably not as relevant as the actual high and low temps that happened, unless you're trying to do some analysis of whether your predictions were right or not. But in a forecast view, obviously the actuals haven't happened yet, and the predictions are highly relevant. And then user preference also comes into play. There are some obvious things here, like what units you like to see temperature in, Fahrenheit or Celsius. Also, a new weather app that I've been using lets you pick if you want to see the feels like temperature all the time instead of the raw temperature, so that's kind of cool. Basically, what I'm trying to get at here is that putting together a set of visualizations of a singular domain of data, whether that's weather data or diabetes data, it's basically a question of figuring out the intersection between two things. So one of those is what you want, and this is kind of where those view determinators have their say, the context. And then what you have, and that's the data that you actually have at your disposal to display and visualize. So bringing this into the Flux architecture, the way I've been thinking about it is that what you want is sort of tracked in one store. I've been calling that a config store. So this is a store for storing and updating the display and visualization configurations. And then you keep your data in another store. So this is where the data lands after being fetched from the server, and it might be constantly getting updates if you're bringing in like paginated data asynchronously or real-time push data. And then you need a place to track the current state of the display. So this is where the elements of the configuration get to interact with the data that's available to display and visualize. So it's also the location to which the user interactions are propagating, so that all that interactivity, like the tooltips, is not encapsulated deep in the rendering code, where it can't be easily tracked, manipulated, or tested. So this is the relationship that I see between these three stores. So the config store and the data store are independent siblings, basically, and the draw store depends on them both to inform its current state. But like all good things in Flux, this relationship is one way. The draw store might be waiting for the config store or for the data store to respond to a certain dispatch, like loading data, before it carries out its own response to that dispatch, but the reverse never happens. One of the main things the config store contains is references to the rendering modules for particular types of data. And then it also tracks the things like the user preferences, units, maybe time zone for display. So here's a simplified example of what the data in a config store might actually look like. So as I said, there's an array here of like rendering modules. They each have an ID, an indication of whether the module is enabled. This is something that I think you could potentially expose to a user as the ability to turn visualization layers on and off. There's also the type of data that gets visualized, and then the reference to whatever module you're using, D3 or React or something, that does the rendering. And then there's the global user preferences that I talked about as well, the units and the time zone. The data store is the simplest of all of them, and there's almost nothing else to say except that it's data, even more data. Just as an example of one way to structure it, in what I've been experimenting with as a possible next version of our data visualization library at Tidepool, I've been grouping the data by type as it enters the data store, and then the data store itself is an object with the data types as keys, and cross-filter objects as values. So cross-filter is a library that's often a companion to D3. It does really, really fast filtering and reductions on large data sets in the browser. And then finally, the draw store is where the information from the config store and the data store intersects. It stores the user's location along the timeline, as well as the data in view at that location, and the datum or data, if any, that the user is focusing on through interaction. And here's an example of what that might look like. So only the enabled render module from the previous config store example got pulled over into this, because the draw store is about what you're currently looking at, so it doesn't care about the modules that aren't currently enabled. And then it's also augmented this module with data. And that would be the data that's currently in view at the location where you're currently at. So this is like a 10-day span of time, so this might be like a 10-day weather forecast view. So one question here is, why not just one store? And this is definitely a place where I'd like to continue the conversation. I think it's probably possible to do it all in one store. Right now, my only answer to this question is pragmatic. And there's a little history, which is that when I first started experimenting with Flux for this purpose, I hadn't really thought through this structure that I've just presented to you. So I had started with just a two-store structure. And basically, the config store and the draw store were the ones that were kind of combined into one, and the data store was separate. And I quickly ended up with some circular dependencies. And when I sort of Googled to figure out what people do about that, the advice was like, OK, well, if you have circular dependencies in your stores, you should combine them into one. So I tried doing that. And I actually did it. I think I had it working for a little while. And then it got really, it was just really complex, and it was really hard to read. And it felt like in some places the logic was getting really convoluted, and that there were these. It's when I started thinking about this idea of what you want versus what you have, and the fact that there are sort of different domains here. So now I've broken it up again into these 3 stores instead of 2, and I've gotten rid of all the circular dependencies. And I'm pretty happy with it. So it seems to be working. But again, I'd love to continue this conversation. So now that I've shown you what the stores look like, I'll briefly just outline for you some of the actions that drive the data flow. So the 3 most important actions for this example that I'm talking about are the initialization of the configurations that you're bringing in, the loading of the data, and then the filtering of the data as you navigate through the time dimension, which is basically the most salient interaction that happens in our interfaces. So the flow is basically that the config store responds to the initialization of the configurations that you bring in. And the draw store waits until it's done, and then it plucks out that information that it needs, which is basically the enabled rendering modules. And the data store responds to any newly loaded data first, and then the draw store will also respond and just pluck out the data that it needs. So that will be the data of the types that the currently enabled rendering modules want. And then the draw store also filters that down to the location that you're currently at, which might be a default location. We default in our daily view to the most recent 24 hours. And then finally, only the draw store is reacting to the actions as you're interacting with the visualization, so scrolling along the timeline. And so here's this in a diagram form. This is a little hand wavy, so don't take any of these lines too terribly seriously. So I've put the init configs and the load data on one side because they're both sort of at the top level. For us in our application, this is kind of what happens when you log in. So there is user interaction that's triggering these, but I've kind of, it's at such a high level that it's not worth drawing in my mind. So the dotted line from the draw store over to this init configs and also the load data, that's kind of how I'm trying to represent the fact that the draw store is going to wait for the other two stores to respond to those actions before it responds to them itself. And then when the user interacts, well, then the draw store is the source of all the state for rendering the visualization, and the user interacts by scrolling along the time dimension and firing off move location events. And then these are dispatched and only the draw store is reacting to them. A lot of other actions are going to be really similar to this move location with only the draw store reacting to the dispatch. So for example, focus data for the tooltips for focusing on something. Again, that's also just going to be something that the draw store is concerned with. And another example might be a zoom action. So the default in our 24-hour daily view of the timeline is the 24 hours. But sometimes you get events that happen very close in time, and you might want to zoom in on them, like maybe a 3 or 6 hour span of time. So we could have an interaction that allows the user to choose to do that. And again, that would just be the draw store changing the default span of time that that view is displaying. But there might be a case where basically almost the same type of zoom action, we might want it to propagate to the config store with the draw store also reacting to it. And possibly, I haven't thought this through completely, but it might not need to wait for the config store to react first. So this is the case where the user doesn't just want to temporarily zoom in to see something, but rather they want to change the default domain. Perhaps this person just likes seeing only 12 hours at a time in the view that we call the daily view. So with this 3-store structure that I've outlined, especially if the config store is perhaps responsible not just for getting the subset of the information that it uses, which is like the user preferences, like the time zone and the units. If it's not responsible just for getting those from the server, but also for updating them and persisting any changes back to the server, then this distinction between the temporary zoom and a more permanent preference change, user preference change, that is the difference between an action that only the draw store is listening for and reacting to, and an action that both the config store and the draw store are listening for and reacting to. So that's actually where I'm going to end, on that sort of optimistic note where I think I've convinced myself again that the three-store structure is possibly really a good idea. So thanks, and again, reach out if you want to continue this conversation. The side project where I've been sort of working through these ideas in actual code is not quite on GitHub yet, but there is a repo with a README. So I'm hoping to put it on GitHub this week. I'm still just finishing up a few things that I wanted to have done before I push it up. So if you're interested in it, keep a watch on that. And then the second link again is where these slides are on the web. So thanks.